Hey everybody. If you're like me, you get a bit confused transitioning from glycolysis to the TCA cycle. There are several little steps and I find that I'm always feeling a bit lost. I wish I could say this video is going to help you move past that confusion, but it likely will not. We are going to take a look at a small portion of what comes between the two processes and make it a bit more complicated than we already know it to be. As you think back to our days of studying micro, you might recognize what's going on in this figure. We have learned that pyruvate is the product of glycolysis, and that it must be converted into acetyl-CoA before it can enter the TCA or citric acid cycle, where it is then oxidized into carbon dioxide molecules. We can see right here. We know that this conversion here happens, but we haven't spent much time looking at the details. In the past, we have always looked at this thinking that NAD+ being converted into NADH is what drives the reaction, and this is partially true. But there is actually a super important enzyme that allows this to happen, and that enzyme is pyruvate dehydrogenase. And I'm actually going to shorten this to be PDH because I don't want to have to say that long phrase every time. So, PDH regulates entry into the citric acid cycle. If you don't know what dehydrogenase means, it describes an enzyme that dehydrogenates, or in other words, oxidizes the reagent. This helps us to make sense of the conversion of NAD+ to NADH. PDH removes a hydrogen from pyruvate, which is eventually transferred to NAD+ in another portion of the reaction. In addition to losing a hydrogen, a carbon must also be lost to form acetyl-CoA, as we are going from a 3-carbon structure to a 2-carbon structure. And as we saw in the previous figure, this happens via a CO2 leaving group. So because both an oxidation and a carbon removal are occurring, the reaction is labeled an oxidative decarboxylation. Okay, here we go. So before we get into the mechanism, I think it is important to understand the structure of PDH. It is actually a huge complex made up of 3 separate enzymes. Each enzyme has a different responsibility, but I want to focus on enzyme 1. The goals of this enzyme are to remove a carbon dioxide group and reduce the remaining carbonyl to a hydroxy group. You're probably thinking, wait, I thought this was an oxidation reaction. And you're right, but the oxidation occurs in the E2 portion of the enzyme. Also, quick side note, the E is not to be confused with an elimination reaction. There are no elimination reactions going on here. In this figure, E stands for enzyme. Hopefully, I'll be able to talk about what happens in the E2 portion next week. And then E3 is a hydride transfer from NAD+ to NADH, which Dr. Barkness already covered, so I won't really be touching on that. But what I want you to focus on is what's going on in E1. Pyruvate losing that CO2 group is what we're really going to take a look at. So on this slide, I have the overall mechanism for what's going on. Well, it just shows the E1 and the E2 portions. This doesn't show the hydride transfer. But by looking at this mechanism, we can see that there is a lot going on with several steps and lots of reagents. So I think looking at the entire process would be too much for a single mechanism talk. So like I mentioned previously, I hope to save the rest for next week and just focus on what's in this blue box up top. I actually want to go back to the previous slide. Well, actually the one even before this, and I just want you to note that enzyme 1 is actually pyruvate dehydrogenase, although the entire complex is named after that. It is truly enzyme 1. So just so that we're clear on that when you're looking back at this PowerPoint. But now here we are at the mechanism for enzyme 1, drawn and labeled so beautifully. I thought this was a great figure. Except for there is one little part that I would like to clarify. So I'm guessing you're wondering where the dehydrogenase is. And I drew it in here as E1. So it's actually this R group is where it's connected to the enzyme, and TPP, thiamine pyrophosphate, is actually a coenzyme required by PDH, but it works in and with PDH to allow the process to happen. So just so that we're clear on that. Also, TPP itself is more complex than what is really shown here. What we can see now is the thiazonium ring. The other R group, the one down here, I can get my arrow to work, the one down here represents an additional ring and a side chain that contains some phosphates, but the thiazolium ring is what's really important for this reaction. So now that we kind of know what we're looking at, we can dive into the actual steps. First, looking at step 1. So the carbon, my arrow is being so difficult. The carbon bound to the nitrogen and the sulfur is actually more acidic than most double bonded CH groups found in other molecules. The higher acidity is due to the presence of the positively charged nitrogen that is able to stabilize the resulting carbanion. The thiazolium ring is likely deprotonated by the other ring within TPP. Although we're not exactly sure how this deprotonation happens, thankfully it's not really vital for us to know how that works. From what we know about organic chemistry, we can see why this is able to be deprotonated relatively easily. So after this is deprotonated and we have our anion, it can react with the pyruvate molecule, and it does it just as we would expect. The lone pair acts as a nucleophile and attacks the electrophilic carbon. Like we have seen over and over again, the electrons kick up to form a negative charge on the oxygen. The oxygen is then protonated by H+, and the nitrogen now isn't particularly happy because it has a positive charge. So what we really want is for that double bond to become a lone pair on the nitrogen. In order for this to happen, the lone pair on this carboxylate group, this CO2 kind of group, this lone pair drops down, and then that allows this bond right here to be cleaved between the C1 and the C2 carbon. So it cleaves, electrons are donated here, a double bond is formed, and then these electrons kick up onto the nitrogen, and our CO2 group leaves. And this carboxylation is really quite favorable because then we're producing a species that does not have that charge, and CO2, as we've seen, is a really great leaving group because it's stable on its own. Now we can move on to the resonance forms in the hydroxyethyl TPP. So we have here on the left a structure that reflects an enamine, and here on the right we have one that looks like an iminium. In the iminium structure, we know that a carbon is not happy with a negative charge, so I would be more prone to say that instead of a lone pair on the carbon acting as the nucleophile, that it's actually the double bond in this resonance structure. And maybe I'm more prone to say this because we just learned about enolates, but I really do think that this reflects the enamine-enolate reactions that we saw in chapter 25. So what happens, if I can get my arrow, the lone pair on the nitrogen drops down, and then this double bond grabs a hydrogen from what actually is, it'll grab a hydrogen from water because this is happening in water. And then we finally end up with our hydroxyethyl TPP, which is the product of this first step in the overall reaction. So then this HTPP will go on to react with another substrate through enzyme 2 to form the acetyl-CoA. But this is where we are going to stop for today as far as the mechanism goes. I also want to quickly highlight that this is an irreversible reaction. So the only step that is in equilibrium is this original deprotonation, But after that, all the arrows are pointing to the right, to the final product. And if we think about this, this really makes sense because we know that cellular metabolism is more one-directional. It's always glycolysis, TCA cycle, electron transport chain. It doesn't go in reverse. We don't go the opposite direction. It's always in that order. The body doesn't convert acetyl-CoA into pyruvate. This is just not what happens. So the reaction is not in equilibrium. It is one-directional from pyruvate to acetyl-CoA every time. One more thing that I would like to point out, I want to go back to this slide so that you can see it, but it's the impact of water and just noting that this reaction happens in water. So here they label it as HA, but really this is a water molecule and it's used to deprotonate and protonate really quite constantly in this reaction, which I think is pretty cool because usually we would use a much stronger base or acid to do these things, but because of the action of the enzyme, we don't need that, which I just think is really, really amazing. So in conclusion, glycolysis and the TCA cycle are really vital to cellular metabolism, but I think it's important that we recognize that so is everything in between. A deprotonation, the movement of a lone pair, the carbon dioxide leaving group, all are necessary and important. So I think a really big takeaway is that cellular metabolism is really quite complex. The conversion of a 3-carbon molecule into a 2-carbon molecule requires several steps, reagents, and enzymes. If one molecule of the enzyme doesn't get protonated, the process doesn't happen. But thankfully, our bodies contain enzymes that react specifically and consistently, so that this conversion can successfully occur in our bodies all the time. So, while I don't always love memorizing mechanisms and learning about molecules like enolates and enamines, I think it's pretty cool that this learning provides us with a window into how complexly God designed our bodies and how beautifully complicated the reactions inside of them can be. So thanks for listening. I can't wait to see you guys again in the fall, and I hope that quarantine is going okay for all of you. All right.